Hi everybody, today we're going to talk a little bit about sleep and dreams. So we've moved into chapter 4 in the text. And the first thing I'd like to talk about a little bit is talk about the circadian rhythm. So they talk about this in your textbook. Basically, the circadian rhythm refers to your biological clock. So this is when are you most awake, most alert, and when do you get drowsy and tired during the day? How long do you need to sleep? So on and so forth. So your circadian rhythm and my circadian rhythm are very different. It depends on the type of person you are, you're a night person or a morning person. And it also depends a lot on the age you are. So your circadian rhythm is certainly different than it was when you were a young child and when you were a teenager and so forth. So it changes over the lifespan, your circadian rhythm. But we're going to talk about the circadian rhythm a bit more and the things that impact it, as well as move in and talk about sleep and dreams. So again, biological clock. One thing that's very interesting that has an impact on your biological clock is light. So the sunlight has a major impact on your biological clock, and research has shown, which is very fascinating, that there's actually, and we figured this out after we did a lot of research on circadian rhythm and light and how light impacts people. And basically we have actually found that for many people, particularly at this time of year, so we're coming right into this time of the year, when we come into the winter months, that it is more likely that people suffer from depression. So we used to think that the reason people suffered more from depression over the winter was because of the holidays and things weren't exactly perfect, and so many people called it the Christmas blues. Research has consistently shown now that it is a true phenomenon. It's called SAD, or seasonal affective disorder, and basically, what this is it's a diagnosable clinical depression that occurs more during winter months, and research has found that about 80% of people who suffer from seasonal affective disorder can actually be treated well with light therapy. So if they get therapy, a light that actually mimics natural sunlight, that they can actually decrease the severity and decrease the even occurrence of seasonal affective disorder. And this is really, really huge, because we talked about in chapter 2, we looked at, antidepressants and the fact that they're impacting your serotonin or your dopamine neurotransmitter systems. And this is a natural, so it is not decreasing the amount that we are producing. It's not impacting the communication between the neurons. This is simply mimicking natural environmental conditions, and if it's helping 80% of the people, that's kind of huge. So seasonal affective disorder, the way we discovered it, again, is when we were studying circadian rhythm, and we found that one of the major impacts of your circadian rhythm and also of your mood is the sunlight. Next, I'd like to just take a quick look at some things that vary in your circadian rhythm. And this chart that we're looking at over here, this chart is dealing with adults. Okay, so this is not in relationship to children, and it would be very different for children or elderly people. But for most people, the peak mental alertness is around 9 o'clock in the morning, and then again at 9 o'clock at night. Again, this will vary depending on whether you're a day person or a morning person or a night person. But this is on average. Our lowest body temperature, so our body temperature varies, is around 97 degrees at 4 a.m. Our highest body temperature is about 99 at 4 p.m. We have peaks in our sense and our ability to sense and our accuracy. and that's around 3 o'clock in the morning, which I found very interesting. 3 o'clock in the morning and 6 p.m. at night. Our pain to sensitivity, our sensitivity to pain also changes during the day, and it peaks around 4 o'clock in the afternoon. So you're more sensitive to pain at around 4 o'clock in the afternoon. We tend to be the most sleepy around 3 in the morning. It's kind of interesting that when we're most sleepy, we also have the peak hearing, visual, taste, and smell sensitivity, and maybe that's because we're sleepy, and so it ensures that we survive and we hear and see the things that we need to, even though we're kind of groggy. And then again, 3 in the afternoon. Oh, so I probably shouldn't be doing this. This is about 3 in the afternoon, so no wonder I'm making a few mistakes. Then we have peak melatonin in the blood, usually between 1 and 3 in the morning. So I just think it's kind of interesting to see all of the different things that are relating to the circadian rhythm and how they change during the day. Oops, I missed a slide. And here I think is a really good example of what's going on and how light impacts. So you can see in this picture, and this is in the textbook, but as light enters in through the eye and through, as we know, the retina, the pupil, the iris, goes to the retina, and then to the optic nerve. It comes from the optic nerve to the suprachiasmatic nucleus, and that is that yellow dot that's right there behind the blue arrow. And that is basically the place where your brain is determining how much melatonin to make. And so there, if there's a lot of light, it's the nucleus is sending information to the pineal gland, and the pineal gland is then sending information to the endocrine system about melatonin, the hormone. And as you know, the more tired you are, the more melatonin you have in your system. So you can see in that top square that when you first wake up in the morning, you can see the yellow. There you have more melatonin. And then shortly after you open your eyes and you get light exposure, the melatonin starts to dramatically increase quickly, helping you to wake up and become more alert. And then during your peak times of alertness during the day, you would see what it looks like down there at the bottom with very little melatonin. So one thing that's interesting about this, I think, and the light therapy, is that they have found that for people who suffer with insomnia, it is very important for that person to be in as dark of an environment as they can be before they want to try and go to sleep, because it will help to increase melatonin levels and make you more tired. Next thing we have done as psychologists is we've spent a lot of time studying sleep, and one of the ways we do that is when the EEG was introduced. So basically, and this is fascinating, it goes directly back to Chapter 2 on the neurons. It is measuring the electrical activity in your brain. So it is measuring the number of action potentials. Because if you recall, action potentials are electrical energy that travel down the axon and push those vesicles up against the end of the neuron and release the chemical neurotransmitter. So this is not measuring the chemical changes in the brain, but the electrical changes in the brain. And you'll see on the next slide how we measure this. You bring someone into the sleep laboratory, and you basically hook them up to an apparatus, and the apparatus, the EEG, will have sensors in all these various places that you can see on the slide here. These top ones are measuring your eye movements. The one on your chin and your neck, so here and here, are measuring your muscle tension. And then the one on your forehead and the one by your ear, those are measuring. That's what we're going to be looking at next. That's measuring the brain wave activity, the electrical brain impulses, and how much activity is going on in the brain, or getting at number of action potentials. So here's what you would see in the EEG readout of electrical activity in the brain. When someone is awake and alert, and I'll switch over so I can mark these with my marker. When someone is awake and alert, you see the alpha waves. And you can see that those are low amplitude waves, meaning they're very short, and that's showing a high level of activity. And as we start to become drowsy, we move from the beta waves to the alpha waves. And the alpha waves, you can see, are taller. So if you look at the amplitude, like here to here, they're taller than the beta waves, and the height is actually showing a decrease or less action potentials in the brain. And then as we drop off to sleep, we will move from the alpha waves, the awake and relaxed, to alpha and theta brain waves in stage 1 of sleep. And then we'll move down to stage 2. In stage 2, you have two unique things that occur. You have K complexes, and these K complexes are where you actually see the amplitude get very large. So the K complexes are showing periods of much slower activity during stage 2, but you can see it's not consistent. It's just much slower. And you also see in stage 2 sleep spindles, and the sleep spindles are showing bursts of activity during stage 2. So stage 2 really is showing the transition between lots of activity like you would have in stage 1 sleep, and then much less activity that you would have in the slow wave or the deeper sleep. And as we're moving from stage 1 to stage 2, we are moving from the thetas from the alphas and thetas to thetas and deltas. So alpha is showing the highest level of activity, and then we move to theta, a little less activity, and the delta is showing the least amount of activity. And then you move down to stage 3, and in stage 3 you will see that you have moved to deep sleep. So we sometimes call this SWS, or slow wave sleep. Deep sleep or slow wave sleep is when you've moved to at least 50% delta brain waves. And so you're predominantly slow brain waves, and you can see the high amplitude and the space between the brain waves, and that is showing, again, a decrease of activity, of brain activity during that time. Certainly not a lack of brain activity, but a decrease in brain activity. And we'll talk about how you move up, but then you go down to this deep sleep, stage 3. We used to have 4 stages. They moved it to 3, so stage 3, 4. If I ever say 4, I'm just talking about 3 now. The slow wave sleep, and then we don't stay in slow wave sleep all night. Then we ascend back, and when we come back, instead of going into stage 1, you'll see these two are at the same level, but instead of going to stage 1, we enter into our first period of REM sleep, and so you've moved back up to active brain, and that will make sense as we talk more about that. Okay, I got to go off the pencil here. All right, so we moved from the beta in awake and alert all the way down to the delta when you're in slow wave sleep, or the deepest sleep that you have. And here I'd like to talk just a bit more about REM sleep. So REM sleep is frequently referred to as what we call paradoxical sleep. Well, first of all, dreaming sleep. First of all, majority of your dreams occur in REM. It's not that you're incapable of dreaming outside of REM. You may have some NREM or non-REM dreams, but the vast majority of your dreams do occur in REM. So REM sleep is sometimes referred to as dreaming sleep. Another thing that's fascinating about REM sleep is it's called paradoxical sleep, and this is where I think oftentimes confusion. We have confusion that comes from what's portrayed in the movies and so forth. If REM sleep is when you're dreaming, REM sleep, you've got a very active mind. So your mind, which makes sense, right? Your mind is active because you're dreaming. You're following this sequence of events in your mind. So your mind is very active. Your internal organs are also fluctuating dramatically. So you could breathe really fast. You will, your heart rate will increase during REM sleep. It fluctuates, so your breathing, heart rate, respiration fluctuate, and genitals become aroused during REM. So internal high level of activation in the brain and the body with the heart rate, etc., but external paralysis. So when you are in REM sleep, this is where the paradox is. A paradox, two things that are very different from one another, they don't seem to go together. With a high activity, the internal high level of activity in the brain and the body going with this external paralysis. So what is basically happening during REM sleep is the dopamine to the motor neurons, we're going back to that chapter 2, the dopamine is blocked. Not dopamine, acetylcholine. The acetylcholine is blocked from being released to the motor neurons. So even though your brain may be telling your body to move as if it was actually, moving in the dream, your body can't do it because the motor neurons are blocked and they're not getting the acetylcholine necessary to create action potentials and therefore muscle constrictions. So paradoxical, internal high level of activity, external paralysis because of the blocking of the acetylcholine in the motor neurons. And then the last thing I'd like to talk about here is talk about the typical night's sleep. And so here we won't look at the first 90 minutes, we just did that, but here we'll look at the 90-minute cycles. So these are the 90-minute cycles. This is the awake and alert over here on the left where you see the green. That's the awake and the alert. And so that's when you're falling off, drifting off to sleep. And that would be where you predominantly have your beta brainwaves. And then as you're going from beta to alpha, that would be here where, and I'll do the pencil again, that would be here. Oops, it didn't take the pencil. That would be here where you're moving from, this is the beta, and now you're moving into the alpha, and so you fall into sleep. This is stage 1 of sleep. Every time that you see these black dots, this is when you are moving around, getting re-comfortable again. So you'll notice when you fall asleep, you stay here a very short period of time, 5 to 10 minutes. Then you drop down from the stage 1 after you've rearranged yourself to stage 2. You spend just a very few minutes again in stage 2, and you descend down. Now you have reached your slow wave or your stage 3 sleep. And then you see you spend quite a bit of time in the slow wave sleep or the stage 3. And then after your almost at your 90 minutes, then you will ascend back to stage 2, stay there for a few minutes, ascend back, shift around in your sleep, and then you enter your first REM period. So it's fascinating that when you fall asleep, you actually have a stage 1, and you will notice that there are no more stage 1s through the rest of the night. The rest of the time when you ascend back, you're ascending back to a REM period instead of a stage 1. So this is stage 1. And these are all REMs. So you have your first dreaming sleep within the first 90 minutes of the night. So you have your first REM period and your first dream, and then you descend back, spend a little bit of time in 2, descend down, spend again quite a bit of time in stage 3 or the deep sleep. But if you'll notice, you're spending less time now than you did the first time, and then again you ascend back, and when you get to the top, well, first of all, when you get here, you shift, then you have the REM, and the reason you shift before the REM is because of the paralysis that happens during REM. So you're not going to move during REM, so your body and your brain get you kind of comfortable, and then you don't move at all during the REM, and then after the REM period, again you shift. and then you drop down to stage 2. You spend a teeny bit longer in stage 2, quite a bit less time in the deep sleep now. And then as you ascend back, you'll notice again, your REM is getting longer with each period. So this REM period is only 10 minutes or so. This one may be up to 15. This one may be up to 30. So, and it depends. This is kind of like an accordion. It can, for each person, depending on your average night's sleep, your average night when you usually go to bed will be here. When you usually wake up will be here. If it's 9 hours, then this will all just be spread out, and each one of these stages would be a little bit longer. Okay? If you only usually get 6 hours, it's not going to stop you here if that's your average, but what it's going to do is shrink this all so that you still each time have approximately 5 REM periods. But your REM periods will all be shorter, your stage 2 will all be shorter, and your stage 3 will all be shorter. So then you descend down, and you'll notice by the second half of the night, basically, you have stopped going down into slow wave sleep. So now you're just in REM and stage 2 sleep. And then you ascend back, and the REM gets longer, and then you descend down, and the stage 2 gets shorter, ascend back, and of course you're shifting every time, REM gets slightly longer, and then here they have you waking up from this. If you are the weekend sleeper, you will basically, what will happen is you will just continue this down. So instead of waking up here, you go here. This is going to be shorter in stage 2. It's going to ascend back to REM. The REM is going to get longer. Oops, sorry. The stage 2 is going to keep getting shorter until eventually you're pretty much all in REM. And this is why you get really tired when you sleep too much, because you are not getting the adequate amount of shift between moving your body and your mind being active. You're spending all of it in really light sleep, so it's just adding a bunch of light sleep to the end of the night. Okay, we're going to stop here, and we'll pick up next time talking more about sleep and dreams.